Welcome to the Fundamental Mechanics lecture. Today we will start a new chapter on the momentum and impulse. This lecture will involve a little bit more theoretical derivations using mathematics than other lectures. So if you like that aspect, you may find today's content more intriguing. And if you're not so mighty in math, that's okay. Just keep in mind the context of where we get our main results from. Our learning objectives are, number one, what is momentum? And number two, what is an impulse? And number three, the energy and momentum principle. And number four, finally, the conservation of momentum. Now let's get right into our lecture. Number one, what is momentum? Momentum is written as P, and that is defined as a product of a particle's mass times the velocity. Now remember, it's a velocity, not speed. Velocity is a vector. Mass is a scalar. So the product of the two is a vector. Momentum is a vector, meaning that the sign matters when you describe a particle's momentum. Now think about, you want to describe a particle's motion, which is an important concept, a quantity that we want to analyze in the fundamental mechanics. If you just put a mass of the particle, it does not tell you anything about its motion. If you just describe velocity, well, it is like abstract arrow on a piece of paper. It is just a vector. It's just a directionality. It does not tell you anything about its subject. So you put the mass and velocity together, and that has, as a unit, that has a meaningful interpretation. Because not only it tells you about the motion of the particle, it also tells you about its mass. So that's why we use momentum in physics as in separate entities. Now knowing about the definition of momentum, let's try to rewrite the Newton's second law. The net force is equal to ma. Now we know the sum of forces, net force, is equal to ma. And we know acceleration is derivative of velocity in time. Now if you take a look at the denominator expression here, and knowing the definition of momentum, this expression is nothing but dp over dt. So now we have a new insight, a new expression of Newton's second law, that the sum of forces acting on a particle, on a single particle in this case, is equal to the change of the particle's momentum in time. Okay, now that is a definition of momentum, and then we will provide some examples in the following. Now let's consider impulse. What is an impulse? An impulse is a force accumulated in time. The definition of impulse is the integral of a force respect to time. And thinking it this way, a force that is short-lived, the force that is applied for a short duration of time, will not have as much an impact, an influence, to the same force applied for a longer duration of time. Impulse is what measures this. Impulse is a force accumulated in time. Now take a look at the mathematical description here. That impulse is defined as the integral of force respect to time. And this means that an impulse is the area underneath the force versus time graph, as you can see in the figure on the right hand side. Knowing about the momentum and impulse, these two concepts will allow us to play around with mathematics to come up with an interesting perspective of motion in nature. Now, when you integrate a force respect to position, in other words, respect to space, that is defined as work, which is equivalent to, as we learned, a change in kinetic energy. Now we know that kinetic energy, the definition is 1/2 mv squared. In writing that little bit, we can quickly realize that if I multiply mass both top and bottom. And take a look at the denominator here. That is momentum square. On the bottom, you have 2m. So you can rewrite the kinetic energy in terms of momentum. Now, knowing that, take a look at here. Change in kinetic energy is a final kinetic energy minus initial kinetic energy. That means I take the final momentum square over 2m minus initial momentum over 2m. Or a little more compactly, I can write that the kinetic energy is really written as 1 over 2m multiplied by change of potential. And here I will take just a p square. So here you have the final minus square minus initial momentum. And that is equal to when you take an integral of a force respect to position, respect to space. It can be written in terms of a change in momentum. Now, a new concept that we'll learn today is a momentum principle. So impulse is defined as the integral of force respect to time. Here was respect to space, here's respect to time. Is change of momentum in time. So you simply substitute here for the force dp over dt. Now you take the derivative, and then you take the integral of the same function. What happens? That cancels out and is simply the integral of dp. And this is 1 times dp, so you have a definite integral between the initial momentum to the final momentum, and you will end up here basically just p from final to initial, which is final momentum minus initial momentum, that is equal to change in momentum. So now we have an interesting principles here. First, if you take a force and do an integral over space, that's how you get a concept of work, which is equivalent to the change in kinetic energy, which in turn you can write in terms of a mass component multiplied to a change of momentum. Now you take the same force, but this time integrated in time. Then what happens? You get the physical concept of impulse, force accumulated in time. Work is a force accumulated in space. And then mathematically, you can see here that boils down to change in momentum. And here, the seemingly two different principles are linked through momentum. Momentum is the one that connects the work energy principle and the momentum principle. A force that you either integrate in space or in time. These two concepts are related and can be described in terms of its momentum. Now, this is an interesting symmetry that the momentum connects these two principles. And again, I know this concept for some of you are a little bit abstract. And that's why I mentioned that if you like the mathematics, these results might be intriguing to some of you. If not, that's okay. Just remember the main results and just remember the context where these things are coming from. And now let's take a look at some concrete examples, how we could apply these concepts to solve. Take a look at a simple example on the right-hand side here. It's asking the cart's change of momentum of delta px. Okay, so before the cart was moving left with the velocity of 2 meters per second, and the mass of the cart is 10 kilograms. Afterwards, it changed going to the right 1 meters per second, and is asking for a change in momentum, which is the final momentum minus initial momentum. Now, what is the final momentum of the cart? That is mv final, and that is equal to the mass of the cart didn't change. The final velocity became to the right 1 meter per second. So let's write that as positive 1 meters per second minus initial momentum. The mass didn't change, 10 kilograms. Initial velocity was minus 2 because it was going to the left. So the change of momentum is 10 plus 20, that is equal to 30 kilograms meters per second. Now let's consider this example. In this example, we're given that a mass of 2.5 kilogram stone is dropped from rest at a height of 3.75 meter, and is asking us what impulse does gravity impart to this stone from the instant it is dropped until it hits the ground, assuming negligible air resistance. Is asking us to solve for impulse, and the definition of impulse is J is the integral of force dt or change of momentum. We can solve this either way, either using the integral of forces or its momentum. And what I'm going to do, I'm going to do both ways for you to show whether the both sides will match up together. So let's first try the integral method. Here the force considered is a force of gravity, and that is with the correct sign, it is minus mg, pointing downward. So then we take the the integral of that is integral of force of gravity, dt, is simply equal to minus mg dt, and t will run from 0 to t. And since mg is a simple constant, you just simply multiply mg to time from 0 to t, and so that result is equal to mgt. Okay, now let's do from the momentum side. Change of momentum is final momentum minus initial momentum. That is the mass times the final velocity minus mass times the initial velocity. And in this case, we already know it was dropped from rest. So this part is equal to 0. So change in momentum is simply equal to the final velocity. Now, how can we write velocity in terms of acceleration and time? Well, we're going to use the first kinematic equation. So you guys remember the final velocity when you have a constant acceleration, which is the case for this one, because we have gravitational acceleration to be constant, is initial velocity plus acceleration times t. This simply means the final velocity initial was 0, a is minus g times t, so you have the final velocity equals to minus gt. Multiply it here, you have minus mgt. So here, I have proven to you that you can solve the impulse in both ways and you should get the same results. Now, to really solve this to the end, how do you get time t? Well, we're going to keep using the kinematic equation. This time use the equation y is initial y plus initial velocity t 1/2 a t squared, the one that we've been using a lot in previously. Here, the final height that when it dropped to the ground is 0, that's my 0 line. Then the initial height is plus 3.75. Initial velocity is 0, so that goes away. But the acceleration is minus 9.8 divided by 2 times t squared. So from here, you can obtain t and plug it in here, and you should have the same answers of impulse for the two cases. Okay, now let's move on to the final point of our learning objectives today, the conservation of momentum. Now, the law of conservation of momentum reads, the total momentum P of an isolated system is a constant, and interactions within the system do not change the system total momentum. Now, I would like to remind you the law of conservation of energy, which writes something very, very analogous to this. it says that the total amount of energy in the system, in an isolated system, is a constant. Interactions, the transformations of one type of energy to a different type of energy within the system, do not change the system's total energy. That was the law of conservation of energy that we learned. Now, for the law of conservation of momentum, just change the wording of energy to momentum and you have the exact same concept. Let's reiterate once again. The total momentum of a system that is isolated is a constant. An interaction within the system do not change the system's total amount of momentum. Now, an isolated system is that there is no external force, an external influence. No one has turned up a heat to heat up the entire system gradually, or there is no bouncing from outside of the system. The system is isolated from environmental issues. In this case, it is also the same that the net force is equal to 0. That is a definition of an isolated system. The net force is 0 because there's no external forces acting on it. Now, from this system, I'm going to now derive the law of conservation of momentum from the system, okay? So inside of the system, there will be many, many particles. They'll be bouncing off each other, flying in all different ways. Let's just consider in a moment, a snapshot, that you have 3 arbitrary particles like this. Okay, from here, just consider particle 1 and 2. You have particle 1 and 2, and they are heading towards collision. At collision, they're going to each exert a force against one another. And let's just call the force that the particle 2 exerts on 1. And here you have a force that particle 1 exerting on particle 2. And what did we learn from Newton's third law? That these are action and reaction pairs, and if I consider this force 2-1 to be negative because it's pointing to the left and this to be positive, they should have equal magnitude but opposite directions. This is Newton's third law. Okay? Now this means that if I add force 1-2 plus force 2-1, what happens? These forces are equal in magnitude but opposite directions, so that will be equal to 0. Now, we're going to now write the forces in terms of momentum. Remember the definition of momentum equals ma, and that we wrote as change of momentum in time, meaning that individual forces, you can also write this, and this is of forces acting on particle 2, so this would be change of momentum of particle 2 in time, plus change of momentum of particle 1 in time, and that is equal to 0. Well, this one is simply saying that when you take a derivative of momentum 1 plus momentum 2, that is 0. What does it say? It does not change in time. The sum of momentum 1 and 2 does not change in time. This simply means that the sum of momentum 1 and 2 is constant. Now, this was an example involving just one particle, but can you quickly see that this would apply to any other particles that are interacting in this system? So instead of just having 2 forces here, you will have many other forces, and all of them would exist in pairs. And that is guaranteed by Newton's third law, because forces either exist in pairs or they don't exist at all. That's Newton's third law. So, if I consider now all the particles in the system, they'll be written this way. You have change of particle of 1 plus 2 dt plus dot dot dot, everything together, n dt. And that will still be equal to 0. And as you've written it here, that means the sum of all individual momentums will be constant. Now, we're going to take one step further. Because the sum of all the momentum, sum of all momentum here, now because the sum of all momentum is constant, I can now arbitrarily define initial state of the momentum. So initial state of momentum 1, initial state of momentum 2, dot dot dot, n is constant. And after some time, after some interaction, they're bouncing back to each other. I'm just going to call the final state, arbitrary state. What is on the right-hand side? Of course, they are also constant. And because they're both constant, now this in compact form is written like this, and then you have the final component written like that, and they're both constant, they don't change, they're equal. So now this expression is a conservation of momentum that we will use for solving problems. Now remember, this is a very analogous situation for conservation of energy, where eventually we derive using the initial state compared to the final state for the energies, right? This is the exact same thing. So if you have a situation involving two particles, let's say, for an example, you will write simply that the initial momentum of particle 1 plus the initial stage of particle 2 is equal to the final momentum of 1 plus final momentum of 2. Now remember that individual momentum state may have changed, but when you sum them all up, the initial up and the final all up together, that summation should remain constant. That's a conservation of momentum. Okay, a different way of expressing this, of course, as we have done with the forces. This, you can either express it this way, or you can also express the change of delta, change of potential was equal to 0 here. That is also the same case here. So you can either write it in this way, or you can also write the summation of all the change of momentum is equal to 0. Meaning that if you have two particles, the change of momentum particle 1 plus change of momentum particle 2 will be equal to 0. These are equivalent relationship, talking about the conservation of momentum. Now that we derived the conservation of momentum, and now we understand where the results come from, let's use the products to solve problems. Example 11.3. Bob sees a stationary cart 8 meters in front of him. He decides to run to the cart as fast as he can, jump on and roll down the street. Bob has a mass of 75 kilogram and the cart's mass is 25 kilogram. If Bob accelerates at a steady 1.0 meter per second square, what is the cart's speed just after Bob jumps on? So here you see Bob is starting from here, 0 meters with 0 initial velocity. He will accelerate a steady 1.0 meter per second square of traveling 8 meters. And he will jump on the skateboard, which was at rest. And we're given the mass of the skateboard and is asking us the final velocity together as Bob and the skateboard jointly move along. This will be due to his initial momentum, and we're given by the law of conservation of momentum that the sum of initial momentum must equal sum of the final momentum. So as in the case of the conservation of energy, just write down these expressions. Just write it down and start from here. This means that the momentum of Bob, the initial momentum of Bob, plus the initial momentum of the skateboard will be equal to a final momentum of Bob plus the final momentum of the skateboard. And this is, of course, the mass of Bob, initial velocity of Bob, plus the mass of the skateboard, velocity of the initial skateboard, is equal to the right-hand side. Now, Bob and the skateboard is one body, so their mass adds up like this, and they will travel with a new velocity jointly. Okay? So here we know the initial velocity of the skateboard was 0, so simply this is the mass of Bob times the initial velocity of the Bob is equal to two masses added together, and they travel with a common velocity that will be different from the initial velocity. Now, we're not directly given the velocity of Bob as he hops on the skateboard, but we do know the distance he traveled and the acceleration during that time. So again, we can apply one of the kinematic equations to our benefit. So final velocity square, that is the velocity that we're looking for here, which is the initial velocity in terms of momentum is concerned, is the initial velocity of the Bob as it starts off from 0 is 0, and then we're given that the acceleration is 1 and the distance is 8, this is 16, so the velocity of Bob is 4 meters per second. And now we have all the pieces that we need. Go back here, we have the mass of Bob, that is 75, and then with that mass he ran to velocity until 4 meters per second until he hops on the skateboard. Afterwards, you have the two masses multiply together, and then we're asked to solve for v prime. And that is simple arithmetic that you can solve. Let's consider another example here. This example concerns about a mosquito and a truck having a head-on collision. So you have a truck that is traveling this way with a certain mass and the velocity, and then you have mosquito traveling with a certain mass and velocity. What would happen upon collision? We're asked, in this head-on collision, which has a larger change of momentum? So we will have two kinds of momentum here. We have to consider the momentum of the change of momentum of the truck and the change in momentum of mosquitoes. Now we're going to consider this to be our system, and there's no other external forces. There's no friction, wind by wind, there's no other forces that are acting on it. We're just simply considering these two to be our system. In this system, the conservation of momentum tells us that what? That if I add them up, they should be zero. That's what the conservation momentum says. Meaning that the change of momentum of the truck is actually the same as change of momentum of the mosquito. They just bear a minus sign, meaning the opposite directions, that the magnitude is the same. So the correct answer here is C. They will have the same change of momentum. But the fate of the truck compared to the fate of the mosquito will be very, very different. How can we understand this? Now, the change of momentum for the truck is simply involves the mass of the truck that doesn't change, and involves the change of the velocity of the truck here. Okay, so I've just written this in terms of change of velocity. And that is equal to minus, I will write a small m here, mass for the mosquito, and he will also bear a change of velocity. And these two, in terms of magnitude, is the same. Let me write this again here, just to give you a visual representation here. The truck is massive. And we have an equal sign. Mosquito's mass is tiny. In order for these two sides to be equal, the mosquito will have to have a huge change of velocity compared to the truck velocity in order to be equal. Does it make sense? Because the truck has much greater mass than the mosquito. That mass proportionality means that the change in velocity that the truck undergoes is much, much smaller than what the mosquito will go through. The mosquito will have to do all its velocity change compared to the truck. In fact, after the collision, the truck doesn't change the direction of velocity. It just keeps going, right? But what happens to the mosquito? This change of velocity is what kills the mosquito, because he has much lighter mass. So even though the change of momentum is the same, their fates are very, very different because of a difference in their mass. Let's now consider one last example. This is one of the homework problems. So consider now a 0.2 kilogram plastic cart and a 20 kilogram lead cart. So you have mass of the plastic cart, that is 0.2 kilogram. And then you have mass of the lead cart, that is 20 kilogram. So you have one plastic cart, and then you have one a cart made out of lead. And they can both roll without friction on a horizontal surface. So they're about to roll. In this situation, equal forces are given. So here, the force is given, equal forces is given on each cart. Not only that, each cart forces are used to push both carts forward for a distance of 1 meter. So same distance, they travel exactly the same distance of 1 meter using identical forces. Only their masses are different. Starting from rest. After traveling 1 meter, is the momentum of the plastic cart compared to the momentum of the lead cart? Is it greater, less than, or equal to the momentum of the lead cart? That is the question. Now, solve a problem like this, I recommend you to use almost like a mathematical proof form, because that in this way you can see how your logic works step by step. Okay, so let's solve that. We know the mass of the plastic card is much smaller than the mass of the lead. That's what we know. We're given that the force applied to the plastic card equals the force applied to the lead card. They're identical forces. Okay, and we're given that the distance, the change in the displacement in both cases is equal. So then, I know the force and I know the information about the distance. What if I take the integral of the force to the displacement? That would be a definition of what? Definition of work done on the plastic card. And this I know is exactly the same because that was the exact same force and the displacement being applied. So I know the work done on the lead card is equal to the work done on the plastic card. Now, utilizing the work and energy theorem, I know this means that the change in kinetic energy of the plastic card equals to the change in kinetic energy of the lead card. Now, this means, of course, the final minus initial for both system here. And since they started from rest, both of them, initial kinetic energy is 0. So this tells me that the final kinetic energy of the plastic card is equal to the final kinetic energy of the lead. Now, does that mean their momentum are the same? And the answer is no. Now recall that kinetic energy can be written in terms of its momentum like this. So this means that Kp is equal to the momentum of the plastic cards square over the mass of the plastic card. That is equal to the mass of the lead card square over 2 times mass of the lead card. Now 1/2 is the same proportionality. Now remember, which mass is greater? It is the mass of the lead that is much greater. But the proportionality is the same. So what does it tell you? You are dividing something with a larger number compared to something divided with a smaller number. This means compared to the momentum square, this has to be larger because you're dividing by the larger mass that is equal to on the other side. And hence, this is a square. This also means, finally, that the mass of the lead card is greater than the mass of the plastic card. Okay, so this is a little bit long-winded way, but this gives you an adequate exposure and an exercise how to solve this problem using mathematical and logical deductions. All right, so review this and let me know if you have any questions. Now this concludes our lecture for today, our momentum and impulse. In our next lecture, we will learn about collisions. Thank you so much for your attention, and I'll see you next time.